All right, chemistry, this is part 2 of your video lecture for chapter 5, section 3. We're continuing to talk about electron configurations and periodic properties, specifically a few periodic trends. The objectives for this part of the lecture, we're going to start with define the terms group trend and periodic trend. That's something that we started to do last lecture. We're going to continue to do that in this lecture. Describe the following terms. We only had one term last time. We have the other 4 this time. I'm going to start with ionization energy. We also have electron affinity. We have electronegativity and ionic radius. Then we're going to identify the group and periodic trends for each of the previous terms. And then lastly, utilize the valence electron model to describe how chemical compounds form. Let's get started. To finish up the last lecture, we talked about ions and what an ion is, the gaining or losing of electrons, giving an atom a negative or positive charge. Ionization energy is a trend that we need to deal with. And ionization energy is the energy that is required to remove an electron from an atom. Okay, so if we are removing an electron, we have to put energy into the system in order to get that electron to leave. Because remember, if we can have an electron inhabit a higher and higher and higher energy level, if we can excite it, we can eventually get the electron so far away from the nucleus that it's no longer bound by that attractive force to the nucleus. Let's look at the trend. It increases. So the amount of energy required increases for successive electrons taken from the same atom. So if I have a particular atom that's electrically neutral, I need to put some amount of energy into that atom in order to remove an electron, therefore ionizing that atom. If I go to remove a second electron, I don't simply put the same amount of energy into that atom to remove the second electron. I have to actually increase the amount of energy that I put into it. And so what that means is that ionization energy tends to increase across a period. Okay, as we increase an atomic number from left to right across a period, the ionization energy increases. It takes more energy to remove an electron. The reason this is, electrons in the same quantum level, okay, n equals 1, n equals 2, n equals 3, electrons in the same quantum level do not shield as effectively as electrons in inner levels. Remember, shielding refers to the idea that the electron-electron repulsion force from one another will actually mitigate or make the attractive force from the nucleus feel smaller. It's not as though the attractive force from the nucleus is smaller. It simply feels smaller because you are, in fact, increasing the amount of negative electron-electron repulsion. So you're simply kind of evening out that attractive force with a repulsive force. We call that shielding. Irregularities at half-filled and filled sublevels due to extra repulsion of electrons paired in orbitals, making them easier to remove. And so that's why you see when you look at the the ionization energies for certain groups, you're going to see that there's a dip or a jump in that ionization energy. That's where it comes from. You're going to see this when you get to half-filled sublevels, okay, where all the sublevels of a particular orbital are singly filled with with one electron, all the same spin. So you guys remember what that is? The other trend we're going to talk about is the group trend. And the group trend is that ionization energy decreases as you go down a group. Okay? Because we're adding layers and layers of electrons as we go down a group, because the quantum number is going up by 1, we are increasing the number of energy shells which contain electrons that shield those outer electrons from the attractive force in the nucleus. If we're shielding those outer electrons from the attractive force in the nucleus, that means they're not being held as strongly. And so it's going to take less energy to remove them. So as you go down a group, we see that those outer electrons are further away from the nucleus and they don't experience as strong as an attractive force, making them easier to remove, making a smaller ionization energy. So let's look at an example here. If we have magnesium and we add a certain amount of energy, for this particular example it's 738 kilojoules, we will remove an electron, and so we yield a positive magnesium ion and one electron, right? That electron that is leaving. But remember, for each successive electron that we remove, the amount of energy required to remove that electron, that one electron, will increase. Notice that in order to remove magnesium's second valence electron, we have to nearly double the amount of energy that we put into the magnesium in order to get it to ionize further, to result in a magnesium +2 ion. But notice this. If we want to remove a third electron, okay, that would result in a magnesium +3, it is possible. It is a thing that you can do. However, notice this huge, steep jump in ionization energy. Notice, with our first ionization energy, 738 kilojoules, we're doubling that for the second ionization energy, 1,451. But we are going to increase almost by 6 times, sixfold, right? 600% increase in the ionization energy to remove the third electron. This results in actually being very difficult to make a magnesium +3 ion, to remove 3 electrons. Because of that, we tend not to see magnesium +3 ions, making the most common ionic form of magnesium, magnesium +2. Again, this is what we see, a table of first ionization energies. Again, when we say first ionization energy, it's how much energy it takes to remove the first electron, not the second or the third. We would call that second ionization energy or third ionization energy. But here we're looking at first ionization energies. Notice that all of these elements that are at the very bottom of this graph, meaning their ionization energies are low, okay, their first ionization energies are low, meaning it requires the least amount of energy to remove that first electron, they're all, you guessed it, group 1 elements. They're all group 1 elements. They have one valence electron in their outer shell. So if you remove that one electron, you've just resulted in a noble gas configuration, because if you're in group 1, if you remove your one electron in that quantum level, you'll actually revert back to the nearest noble gas configuration, which is stable. But notice each of the highest energy or ionization energies in each of these periods is the noble gases, or are the noble gases. Helium, neon, argon, krypton, xenon, and radon. These are elements that are so difficult to remove one electron that they tend to not. You very exceedingly rarely see ionized forms of these elements, so much so that go so far as to say you will not see them in nature. Here's another way of looking at ionization energy. If this makes more sense to you, getting a little bit three-dimensional in our representation. First ionization energy, the taller the column, the larger the ionization energy is. And so we see that as we go, start with group 1, okay, 1A, or the main group 1. If we start up at the top with hydrogen, we see, medium high ionization energy. But if we go down one group, if you guys remember from an earlier slide, the ionization energy should decrease. Notice it goes down a huge amount. Okay, a huge amount. And so the ionization energy for lithium is very low. Sodium is very low. And we're actually going to continue to go lower. For potassium, it's low. Rubidium, it's lower. Cesium, it's even lower than that. If we move over to the right, okay, if we move to the right, we're going across a period. Let's just start, for example, at sodium in A. If we move to the right to magnesium, that first ionization energy is greater. Okay, ionization energy is going to increase. Now, if we jump over to aluminum, from this angle, it looks like it's decreased a little bit. Okay, that's all right because this is just a trend. We're seeing a trend. As we move to the right from aluminum to silicon, we see that the ionization energy goes up. As we go over one more to phosphorus, it goes up. Sulfur, a little bit debatable right there. But then when we go to chlorine, it goes up yet again. And then to argon, going up yet again. So we see this overall trend. of ionization energy decreasing as you go down a group and increasing as you go to the right across a period. Next trend, electron affinity. Electron affinity is a tricky one to wrap your head around because some semantics come into play, and we'll get to that. But electron affinity is the energy change associated with the addition of an electron. So ionization energy is the removal, removal of an electron. Electron affinity is gaining an electron, the addition of an electron to an atom. Affinity tends to increase across a period. As you go from left to right, the affinity increases. Affinity tends to decrease as you go down a group. It goes down a group. This is because, again, we need to remember why these things are happening. Electrons further from the nucleus experience less nuclear attraction. Because as we go to the right, across a period, we are truly increasing the amount of positive charge in the nucleus, increasing that attraction to the nucleus. But as we go down, we are, again, adding shells. We're adding shells. And so the energy change associated with adding an electron to something that's very, very far away from the nucleus is not going to be very great, because it's going to be a weak attraction being much further away from the nucleus. Why is it far away from the nucleus? Because we're very far down a group. We have a lot of energy shells. We have 4, 5, or 6 energy shells, and that's going to mitigate the attraction force that electron is feeling towards the nucleus. We are going to see some irregularities due to repulsive forces in the relatively small p orbitals. So when you get over to the p block, there will be some weird things. You guys know that some of them in the tables in your book show zeros. You see some ups and some downs. But again, pay attention to the overall trend as you go all the way across the period or down a group, and you'll see the trend that you are responsible for knowing. So again, if we have this change from boron to carbon, see it's decreasing from oxygen to fluorine. See a decrease. Now if we go over here to aluminum, atomic number 13, we're seeing that electron affinity as we go from aluminum to silicon, again, which is going from left to right across a period, we see the decrease. That's what we would expect. However, we see a bump up as we go from silicon to phosphorus. It goes from silicon to phosphorus. And this is going to be a little bit difficult to wrap your head around, but again, the overall trend is that these numbers, these electron affinities, are becoming more negative as you go across. And that is the trend that we want to be familiar with. And I will not be testing you or quizzing you on exceptions to the trends unless I specifically tell you I'm going to quiz you on them. And this will not be one of them. Moving on to the next trend, ionic radii. Same idea as atomic radii, but instead of looking at electrically neutral atoms, we're looking at charged ions. Again, there are 2 types of ions, cations, which are positively charged ions, and these are going to be smaller than the corresponding atom. Anions, the negatively charged ions, are going to be larger than the corresponding atom. Now, let's look at why. When we have a cation, it's positively charged. That means that we have lost an electron. When you lose an electron, the amount of attraction force that the nucleus is giving out, that the nucleus is having on the electrons, doesn't change because the number of protons hasn't changed. What has changed is the amount of shielding that the other electrons around the nucleus are going to be experiencing. And if you have the amount of shielding going down, that negative electron-electron repulsion, you're going to allow those electrons to settle in closer to each other because the amount of negative charge has gone down. If you allow the electrons to settle in closer to one another, that's a smaller radius. On the other side of the spectrum, we have the negatively charged ions. Why are they negative? Because they gained an electron. And again, the amount of positive charge in the nucleus is not changing. The number of protons is not changing, so the amount of attractive force doesn't change. What is changing is the amount of shielding experienced in the electron cloud. And because we're gaining electrons, the amount of shielding is increasing. And so we're going to see an increase in the amount of distance that these electrons want to have from one another, and they are going to spread out as a result of that. Having your electron cloud spread out means your radius is getting larger. So I have a couple of graphical representations of these trends that you definitely want to keep an eye on as you're studying and preparing for the assessments for this section and for this chapter. This is a summation of periodic trends. We see electron affinity increasing as you go across a period. We see ionization energy increasing as you go across a period. We also see ionization energy increasing as you go up a group. We also see electron affinity increasing as you go up a group. And then we also see atomic radius going, excuse me, we also see atomic radius increasing as you go down a group. And we also see atomic radius increasing as you go to the left across a period. Okay. Now, in the future, we're going to be talking about metallic and non-metallic character in a little bit more depth. The only thing I'd like to point out about that right now is, yeah, the nonmetals are over on the right side of the periodic table, and you're going to see that non-metallic, non-metal character increases as you go that way. The metals are on the left side of the periodic table, and so obviously metallic character is going to increase as you go that way. Here's a table of ion size, and we're going to see our trends in play right here. We have lithium +1, we have beryllium +2, we have oxygen -2, fluorine -1. And yes, this is a graphical representation. Please use this for your reference. And here I got a really, really funny joke here. Go ahead and read this. You're going to have to do the work on this one. That's a good one. The last trend, electronegativity. This is going to be a huge one for the rest of this course. Electronegativity is the measure of the ability of an atom in a chemical compound to attract electrons. Attracting electrons that aren't already in its own atom. Okay, attraction to electrons outside of its own atom, which is also going to be relative to the overall attraction force that the electrons in that atom are feeling all the time. Electronegativities tend to increase across a period. So as you go from left to right, okay, as you go to the right of the periodic table, you're going to see that these increase, meaning you're going to see a stronger hold on electrons, a stronger attraction to other electrons as you go to the right in the periodic table. Electronegativities tend to decrease down a group, or at the very least stay the same. But in general, we're going to say that they decrease as you go down a group, because remember what's happening as you go down a group. You're increasing the number of energy levels, increasing the number of shells. When you increase the number of shells, those outer electrons are further and further and further away from the attractive, positively charged nucleus. And because they're so far away from the nucleus, they're not being held as strongly. And if those electrons aren't being held as strongly, you're also not going to be able to exert an attractive force on other electrons, in other systems. This is going to be a reference table that you are going to want to use for your quick write for this section. This is a periodic table that lists electronegativities. Electronegativities, these are not true numbers. They're arbitrary. Okay, they're arbitrary. These are just assigned their relative numbers to one another. They're on a scale of 0 to 4. 4.0 is the highest electronegativity on the periodic table, and is held by fluorine up in the top right of the periodic table. All right, guys, I know this is a lot to take in, but remember, you're going to need to remember what each of these periodic trends are and why they are the way they are. I will see you next period.